Alright, hi folks. Welcome to another stream of me working on a Casio Loopy Emulator. So I've done a bunch of stuff since the last stream, so I guess as a start I'll just go through some of the commits and sort of show what I've done. First thing, I'll just run the binary here so you can sort of see. One of the first things I did was I made it so that the color on the left here is yellow. Yeah, let's just move the audio here. Make sure that people can hear me. So I implemented disassembly for all the different instructions. So you can see that here. This is actually disassembling the entire 2 megabyte file. So the end is all just this FFFF, but you can see this is what we were disassembling before, starting at 480 here. I don't know if this font is too small. Let's see. Maybe I'll make it a little bit bigger, just in case. Maybe there. So yeah, so we can see the instructions here. I did a few passes to make sure that the instructions are right. And then we can also see some interesting stuff here. So in this case, it's saying move from this location into R0, and this is what's at that location. So you can see this is 488, and if we look at 488, we'll see 09800, and that's what's here. So that's just a convenience thing, so that we don't have to sort of like trace down these references ourselves. Because this is in ROM, we know that those values will never change, so that's it just makes it like easier to read. So that's what's happening here as well. It's just showing us that it's moving these values here. This one's a bit weird because it's actually moving the address, but it still is showing us what the value is there. So what's happening is it'll move the address, and then this instruction where it does the at R0, so basically loads this address here, and then this one actually loads that value into R15, and then this one loads the value into VBR. And so I did a little bit of reading in this doc here about what all these different values mean. R15 is the stack pointer, so that gives me an idea that this is probably the extent of what you get from RAM. And VBR is actually, they call it the vertex register. So, not vertex, vector. So basically that means that whenever you have an exception, it basically looks up whatever's in the VBR and then uses that as the branch point. So in this case, we can see that it's actually using E000080, and that's basically right up here. And so what's interesting here is you can actually see that this looks like a big table of addresses. And so the addresses here are all 00000604. And so they're all 4-byte addresses, and most of them are all the same except for this one here. This one is a little bit different. So you can see that this is actually AF3C. So if we actually go down and we look at that, you can see something that looks kind of like reasonable code. So basically what's happening here is R15 is our stack pointer, like you said, and we're pushing a bunch of values, basically storing the state. Then we load up some values, and then we jump to a new function, and then after that we pop all our values, and then we return from exception. That's what RTE means. So what you can see is that like the code here actually kind of makes sense, which is cool. So that's the current state of things. I was hacking on some additional stuff, but first I'll just go through the Git changes. So I think where I ended the stream last time was, let's see, where did I end? I guess I streamed on Tuesday? I'm having trouble remembering here. Oh yeah, okay. So actually I did a bunch here. So let's just curious, are you documenting memory maps registers with cold homebrew developers, cough cough? Yeah, I definitely am going to start doing that. I probably should take better notes. Right now it's just kind of like all in my head. But yeah, I will definitely keep notes for this stuff. I'll probably also cheat and use some of the information that has been gathered in the MAME port. But for now, I'm just going to sort of try and figure out what I can figure out on my own, and then only sort of go to that when I'm like, oh, I have no idea what's going on. There's going to be a bunch of other work to do in the meantime, so I won't have to go read stuff on stream that will be boring for most people. And yes, oh, hi again. So yeah, let's just take a quick look at some of the commits here. So this one, happy to help with documentation. That'd be so awesome. Yeah, that'd be super helpful. So this was basically me finishing up some of the instructions from before, and I found that the doc has like a lot of useful stuff here. So actually, I was kind of doing it a really stupid way and trying to figure out like what the instructions were. But if you look at the bottom here, there's actually like instructions by opcode. So I could have just used this, and that would have been super simple. In any case, that was what I was doing here, was just implementing a few more of the instructions. Let's take another look. Then here, I basically finished them all off. I think I did this that night, like afterwards, because I was just like, why not just finish them all off? So this is the rest of the instructions there. Not much to talk about, but that basically got them all working. Then I did some cleanup on the decoder. Oops, let's just show you that. And so mostly that was just sort of, yeah, making it look a little bit prettier so that I could sort of see how things lined up. So you can see, like, rather than having it sort of splayed out like this, I kind of made it into this nice little compact form. I like having things compact like this because it makes it easier for me to sort of see like how everything lines up. Let's see, and then, well, I can go through every commit, but honestly, it'll be easier to just take a look at the code. So let's take a look. So the biggest change that I did here was I made this sort of giant macro page here. And so what this is doing is it's showing all the different types of operations that we have and then giving them a code. And I sort of came up with a weird format for this. Basically, whenever you see something that's like, let's go back to the top here and I can show you how these line up. This is, yeah. So this is the instructions by name. So you can see here, I tried to actually have it map to the same order, pretty close anyway. So here you can see add rm_rn, that's this one here, add rm_rn. Then we have add i_rn, that's add immediate. And then we have add c and add v and so on. And so some of them get weird, like this is and b. IAR0GBR. That's this one here. So the I is immediate. I call this @ A. ROGBR is sort of like that's how you do the addressing mode and so on. And so then I put sort of a nice little formatting here as well. So you can say the operands have a pair. The first one's an immediate. The second one is an @2, and that's what I'm calling this @2 because it's got 2 parameters. And then you can pass in the 2 parameters here. And that just makes it so that it's a little bit easier to sort of read through and be like, oh, okay, I know what this is actually supposed to be using as its operands. And so those use these macros here. They're just little magic macros that create a format string for the disassembler. So then, what's cool about this sort of magic macro stuff here is that it allows you to sort of make a nice little table, and then you can use that table in various places. So what I'm doing here is I just have it generate a list of all the different operation enums, and that's basically just this column here, the first column, the 0th column. So then each of these has a different format, in each of the instructions, and those map up to the formats here. So you can see format 0, format N, format M, NM, and so on, right? And that's what we are listing here. And that's the first column right there. This is some new stuff that I'm working on. I'll talk about that in a bit. But basically, This is a RISC chip that's pipelined. So each stage of the pipeline, basically when you execute an instruction, each part is executed independently, and it's all just kind of shifted down. But yeah, I'll get into more details about that later. So then I added a memory map. That's what this is here. This is basically just mapping out the different areas of memory. So actually, I should make this a bit clearer. This is basically from here to somewhere. Basically the size of the ROM. All the ROMs that I've seen so far are 2 megabytes in size, which I believe is that. Is that right? I don't know. That's 64K. It should be. Yeah, I don't know. I think that's right. I'll check it. I'll leave it off for now because I don't know. In any case, I did some investigation and found that this is definitely the address where ROM lives. So, but I don't know where anything else lives. Like I said, I have a guess that RAM is at 9, but I'm gonna postpone that for now just because I'm not sure. And so then for each instruction, I have some information about it. This is the format, which basically we talked about before here. But then we also have the operation string, which is kind of like the name. That's the second column here, or the third column. We'll do one-based indexing. So that's basically the name of the instruction. And then the format string, and that's the one that's actually being generated here. And then inside the instruction, we have information about like the specific instruction that we decoded. So in this case, a lot of the instructions have an N and an M, and that's what's going on here, N and M. Some of them have this D, this displacement, and that's what this D is here. And then some of them have an immediate value, like this I here, and that's what this I is here. And then because op is 250, it's an enum. This is going to be 1 byte, and so this is 3 bytes, and so then we pad out to 4 bytes just because might as well make this nice and small size. Okay, and so then more pipeline stuff. We'll talk about that later. And then I made a sort of struct for all the different registers, so we can look at the registers here. So this is all 16 of the general purpose registers, and then there's SR, GBR, VBR, Mac, MACL, PR, and PC, and so you can see them all here. One thing that I like to do is rather than have something like SR where you have to like individually write the bits in, I find it easier to just store those as bool, and anytime you actually want an SR, then you just generate it at that point. My guess is that we're going to be accessing T a lot, so we might want to put that at the top of the registers. I don't know. We'll see if we need to. So the next thing we have here is the emulator state. So for the did I lose my stream? No, it looks all right. So for the Game Boy emulator I worked on, this actually turned out to be a really cool thing to do, is to basically have it so that the state of the emulator that can change is in one structure. That way you can basically do a save state by just blitting out that structure directly. And anytime you want to do a load state, you can just load that structure. So then finally, the emulator has the ROM, which does not change, and then the state. So that's basically what's going on here. Like I said, I changed a little bit about how this stuff works. So now we have this map address function where you can basically look at an address and then try and determine where it is in memory. And so for now, I'm just looking at ROM. I should probably create a enum for this, but for now, I'll just leave it like this. And then this is actually how you read a 16-bit value. I'm pretty sure that the bus is 16-bit, and so I think I want everything to basically funnel through this U16 read. Even byte reads will. So basically what will happen is you'll do a U16 read, and then you can like mask off the part that you don't want. And I think that's actually what the hardware will be doing in actuality. Like if you read about how it does instruction decoding, instruction fetch, it actually will read the parts independently. So actually, maybe it has. Well, we might have to revisit this. I don't know. It might actually be a 32-bit bus. Okay, and so then finally you can see this is what the print instruction looks like now. And it's actually very cool because it means that all the information that we need is inside this instruction structure here. And then we can basically pull the data out. And this means we can actually use the same decoder for the disassembler and for the execution. Because all it really is doing here is it's just like building up this structure with the data that goes into it. And so then this is the actual decode function here, which is similar to what we had before, but actually basically just packs in the information that it needs about what actual instruction is. So for this stream, what I'm going to be doing is working on the pipeline and then trying to do some initial instructions. So if we look at the documentation for the pipeline, I think it's down here. Yeah, there's a lot of complication that we're not going to have to get to right away. I just need to do some of the basic pipelining. So let's see if I can find. Yeah, there's a lot of pipeline stuff. Yeah, here we go. So the basic idea of the pipeline is this. You have a number of instructions. They have a number of different stages, and each stage has a slot. And to make the CPU run as fast as possible, you want these stages to be sort of working at the same time. And like the normal way that in sort of an older CPU would do this is that you would do all of these, and then you'd wait, and then you'd do the next instruction, and you'd wait, and so on. And by pipelining, you can sort of like overlap it. And so now the instruction fetch part of the pipeline is not, it's able to do work more often. Instead of having to basically wait and then reuse it down here, it can sort of shift over. And this is sort of like, you know, pretty common thing. And you know, this CPU is from 1995, but it still was like pretty, you know, pretty important to be able to do something like this. So I don't know if we're actually going to need to emulate the pipeline accurately, but I figure because we don't really know a lot about the system, it's better to try and match the actual behavior of the system as close as we can. And then if we determine later, like, oh, actually the behavior of the pipeline and like so on isn't that important, then we can maybe do some optimizations there. But for now, I think it's better to try and match the actual behavior of the system. So to do that, we basically want to have the same idea where we have a collection of instructions that are being executed, and then every step, what we do is we're doing the you can't see when I touch the screen. Every step, we're basically doing the execution for a particular slot. So in this case, let's say we're at this slot right here. What we want to do is do the write back for this instruction, then the memory access for this instruction, then the execution for this instruction, then the instruction decode for this instruction, and then the instruction fetch for this instruction. So basically we're doing all of the work exactly the same way that as close as possible to the same way that the CPU would be doing it. So that's what I'm going to try and do now. And so there's two ways that I was thinking about doing this. You could either factor it so that each, how do I say this? You could factor it so that basically we're storing each instruction as it's going through the pipeline, and we keep track of which stage that instruction's at, and we execute it, and that's what I've currently written. But another way to do it is to have each stage be its own structure, and then sort of pass the instructions to the different stage. And I have a feeling that actually might be the better way to do it. And I'll talk about a little bit about why I think that is. One of the issues with the pipeline is that certain things can break the pipeline. So, for example, what they talk about here is that there's a memory access, and then there's an instruction fetch. And both of those use the memory bus, and so they can't actually be in the same slot. So what happens is, if they were to be in the same slot, then the CPU actually creates a bubble here where it pushes this instruction's slots over. And then so you can see it separates the memory access and the instruction fetch. So what we actually want to do is that when we're executing, like let's say we're executing slot D, what we'll do is we'll execute the memory access, and then we'll sort of make note of the fact that we did that. And if we can tell that there's an instruction fetch that would happen, then we actually need to prevent these guys from being executed. So I think it's better to be able to not have to scan through all the instructions to do that, but instead just look at the instruction fetch pipeline and say, do you have an instruction right now? And if so, then basically say, okay, defer these operations. So what I think that means is that the way that I've currently structured this is not really what I want. Because what I've done so far is I have a pipeline, and that has an instruction and a stage. And the stage is basically the stages that we talked about here, the instruction fetch, decode, execute, memory access, and write back. But instead, what I think I want is to not have a generic pipeline, but actually have the different types of pipeline as their own structures, and then we'll store each of those independently. So we'll see how this works. So what I'm going to do is call this one stage IF. Yeah, I think that's fine. So stage IF basically stores the information that it needs. Stage ID, type def, stage EX. Also, if anybody here has written an emulator where they've done pipelining, I would be curious your thoughts about it, because I'm just sort of going based on what makes sense to me, but I have no idea if this is actually like the right way to do it. So I think what we'll do here is we'll store the instruction code. Here we'll store the decoded instruction. No, is that right? What we want to store is the information necessary for that stage, right? And we want to push the information to this. So in this case, we don't actually want to store that. We want to store the address to read from. And this one we store, yeah, how do we want to do that? Yeah, okay. I think we can do, I mean, it's a bit weird here because what it's saying is, yeah, this is the data that you need. All right, well, we'll go for this for now and see how it works. So that's the instruction that's been decoded that we want to execute. And then here we have the memory access, so that would be the address that we want to access, and then the data that we want to use. So in this case, it would be, what I think you want is to actually store the operation so we can tell what kind of, we might want this to actually be a memory access type. That might be better. Yeah, so this will be memory access type, we'll call it type. And then this will be the value. So we'll just make this a union of all the different values that we could potentially have. So this will be, we'll call it UA-val. I kind of want to just call this 8, but you can't. I don't know what you call it. Something like this. Maybe. I like to keep the names short just because we're going to see them a lot, so I want them to be simple, easy to read. And then the write back, that's basically when you've actually done the operation and you want to write the value back to the register. So we need to know, the register to write to, that's the register number, and then the the value to write to the register. Yeah, I think that looks correct. So then we can get rid of this. This is basically now all our different stages. So we have our, and we can't call it if because that's obviously the name of a keyword. So we'll do it like this: stage memory access, stage write back. Okay, and then our pipeline is not 5 anymore, it's just 1. And we have all these different stages. Yeah. Okay, this seems kind of cool. So basically what will happen is, we'll first, yeah, this address, this probably doesn't actually need a stage. Because I think it'll end up actually just, we'll just write directly into the code here. We need a way to be able to say whether or not a stage is active. So I'm going to do something like this. We'll see if this makes sense. I think it does. Yeah, okay. So now we have our state, which is our pipeline here. We'll go down to our pipeline. And so now, rather than looping over these, we'll actually just pull out our pipeline like that. And rather than switching, we just actually do the update for each of our stages. So this will be stage instruction, oops, stage instruction fetch. And I think, is there ever a case where we're not doing an instruction fetch? I don't know. We'll have to see. So then we'll do stage instruction decode, stage execute, and actually we'll just call this stage fetch and decode, stage memory access, stage write back. I think we'll have to pass the entire pipeline down because we want to be able to have a stage right into the next stage. Oh, actually, let's see. Yeah. No, I think this will be all right because what'll happen is it actually needs to be in the reverse order. Because what's going to happen is this is going to be like we're executing this slot here. So it's going to do the write back, then the memory access, then and so on. And the reason this is going to work is that stage write back is basically going to say, do my work, and then my data can be blown away. And then stage memory access is going to say, okay, do my work, then write the information to write back. So I think it all works in that case. So now we'll pull out these two. And then this is what I was doing, was the fetch before. Fetch comes before decode. So, so this is not right anymore. So I'm just going to get rid of this code here. Yeah, so basically what fetch is going to do is it's going to look at the current PC, then it's going to read the code, and then it's going to write into the instruction decodes code, the code that it read, like that. I think. Oops. And we can just pull this out. Oh, and we need to pass the emulator here too, which means that probably we don't need to pass the pipeline because we can just pull it out. Like that. Okay, so then, oops, we have, we write into here, and I'm going to get rid of this for now and go back up to the top so that we can see how we structured this. Right, and we want to say, yeah, is the fetch ever not active? That's what I'm not sure about. Oh yeah, no, of course it is. Yeah, it would not be active if, oh, but it's, well, it's still active. I don't know. I have to think about this. In any case, we know that in this case, pipeline ex active is true. So we've decoded the instruction, so that looks good. And then, oh, and we want to read from our pipeline, so we'll do e pipeline, and then this will be e pipeline, like that. And so then this is reading e pipeline ID code, like that. And then the execution, that's going to be where all the work is being done, basically. So we'll do that in a second. And then the write back actually should be pretty easy. I think this one is just e pipeline. Actually, we don't do anything with the pipeline. We have our register. I'll just make sure. This might need to be more than just the general purpose registers. So, in fact, it almost, well, I don't know. I'm gonna have to read more about how this works to figure it out. So for now, I'll just leave it blank. Yeah, so then here, we're actually gonna switch on the pipeline. We should choose that one. The instructions operator, and that's going to be one of these ops. So the very first op we can go back to here, and this isn't going to work, but we can at least do this. So the first one, assuming that we're starting at 480, which I think is pretty reasonable because that looks like it's the start, is this instruction here, which is, it says it's a move, but it's actually move A. So, and the reason it's printed out that way is because it's moving the address of based on a PC relative location. So I'm going to do that one first because that's the very first one we're going to execute. And we'll do it like that. So move A will be the instruction that we execute, and we'll figure out what exactly that does in a second here. Let's bring back our thing here. Hold on. Yeah, there we go. So we can look at what it says move A is supposed to do. Here. Move A, right. So here's what it's supposed to do, which is pull out these values here and then write it into register 0. It's always register 0. And so our decode is actually already calculated the disp value. So we really just need to write into register 0 and then we're done. So I'm going to do that here, which will be e state reg r0 equals e pipeline ex inster d, and d is our disp. And then it's got to move the PC forward. Where does that actually happen? Does it actually happen here? I think it might actually. Well, let's think about it. So if we're executing the instruction, we're already in the EX stage for this instruction, and we're already fetching something later. So what's the real PC? The real PC shouldn't change until you execute. No, that's not right. The real PC changes when you fetch, I think. Yeah, I'm not sure. Because basically what's happening is when we do our decode, we're already taking into account the fact that, like, if we look at our move A, we're passing in our PC here. Our PC is expecting to be, it adds this 4 in for us. Because essentially what's happening is the PC at the time where it's executing is ahead by 4. When you decode, it's ahead by 2, and when you fetch, it's ahead by 0. So I think it's probably best to increment the PC every time you do a step. And then the PC is always accurate. But then the problem is the disassembly is wrong, which we don't want. So yeah, I think what we actually want then is that when you execute, yeah, this is tricky. Well, I have to think about how this actually works. Yeah, I think this is gonna. I think it's gonna do it here. I think that's the only way that makes sense. So this would be, but that's only if the execution didn't move the PC. Which means the yeah, this is a bit tricky. This is trickier than I thought. Okay, because basically what's going to happen is we want to execute it in this order, but when we do stage execute, that might be a branch, which would move the PC somewhere, and then we don't want to move it again in the fetch stage. Yeah, I'm gonna have to see how this actually works. Let's see. So if we look at how the pipeline is, whoa, what's going on here? If we look at how the pipeline is actually set up for, I want to see for like a branch instruction. So it's Mac RTESTSL. Okay, branch. Yeah. So when the condition is satisfied, it did a fetch here, it did a fetch here, and then it fetches from the new address here. They're fetched but discarded. So in a sense what's happening is the PC is updated here, but then it's updated again. Fetched but discarded. That's interesting. Yeah, so basically we have to know that when we branch, we have to we throw away our decode, and then we fetch, but we throw that away too. So it's kind of like the same sort of bubble that we have with memory access. We have to sort of like say, okay, we changed the pipeline. Okay, so that makes sense to me. So then to answer my question, as to where the PC is incremented, I think it is inside instruction fetch. It just means that at this stage we throw away that fetch. So what would happen is we do a fetch, then we bump the PC, then we do a decode of whatever we've got in there, then we do another fetch and bump the PC. Then we do an execute of this branch, which moves the PC, and then we do this fetch, but it's a special fetch which does not bump the PC. So what I'm thinking is that we actually do this, but then we need a special we need parameters to stage fetch, but I'll do those in a second here. So this is the actual instruction that gets executed here, and then these ones do nothing. So I think this would be enough to do our first instruction. I think so. So what we'll do is we'll actually we'll disassemble, but not 1,000. We'll just disassemble. Well, first I want to start the emulator and set the PC to our 480 here, and then I'm gonna disassemble from PC, and we're gonna disassemble just a few instructions. So like, let's say 32. Let's see if this builds. Nope. So we have to fix a bunch of stuff. Okay, we don't have a memory access type. I'll just add one here. I don't know exactly what that's going to be yet, but we can look at it later. It's E-state pipeline. These names are getting pretty long, so I might want to have it so that we can shorten them, but for now I actually kind of like seeing how it's all nested. PC undeclared, right? This is E-state reg PC. And this is state invalid op. Okay, so a bunch of stuff isn't handled in the switch, of course. So we'll just make a type, and we'll just make this blow up. Okay, that builds. Okay, so now if we run, we decode our instructions there, and yeah, that's our first instruction. So we're not actually showing anything while we're stepping, so I'm just going to do, have I been using fprintf? Yeah. Let's just do it on std out, actually. I want to print out where we're at the PC, so I'll just do that. And then I want to print out the instruction. So actually what I want to do is just disassemble where we're at. So what I'm going to do is, yeah, I'm going to change this so that we're not actually doing it there, we're doing it here, and this is PC, and this is just going to disassemble the one instruction. And this, whoops, this needs to be that now, and this is that. Okay, so it's printing nothing because I'm not calling step. So now, call step, pass in the emulator, and I have to take the address there. Okay, so it printed the first thing, and then it failed. So that's because, I'm gonna get rid of this again. That's because we are trying to execute, but this stage isn't active. So what we'll do is if the pipeline, if it's not active, oops, not continue, return. And we'll do the same thing here. And we'll do the same thing here. And actually, maybe this is the way that we handle a bubble, is we just set the stage to being inactive. That might be enough. So let's do that. Okay, so now it's blowing up there. And probably, I zeroed out everything, so those should be inactive. So let's just do a quick trace for all of these. Okay, so we do write back memory access execute. So why is our, oh, right. This is the type of dumb mistake that you only make on stream. Okay, so cool. We did one step and it looked like it was okay. So now if we do 3 steps, right, so it's executing the same thing each time. Why? Wait, actually. Oh, it's because I never set the instruction fetch to active. So yeah, let's do that here. Active equals true. Fetch, fetch, fetch. Okay. So then this needs to set, yeah, this needs to set this to active. Okay. That actually looks pretty good. So what happened was we do a fetch, and then we move on here, then we do a decode of this guy, and we do a fetch for this guy, and then we do an execute of this one, and we decode that one, and then we're fetching this one. It's a bit confusing. We probably are going to need to have a better way of expressing like what's going on in each stage, but this is sort of giving me an idea. So we executed this, and what I'm going to want is actually ability to Yeah, probably going to want to be able to print registers. There's like, there's a ton of register information, so I don't want to print it all out. We might need to start working on what we want to do for debugger stuff, but for now, this is probably fine. So let's take a look at our registers again. I'm going to only print the registers that we know are useful. So I'm not going to print like everything, although I think we're going to have to start doing VBR and all that stuff pretty quick, so yeah. I'll call this that, and actually let's do maybe something like this. Just do it the same way as I normally do. Print these out like that. This is just like dumb formatting crap. So this should be I. This would be E state reg R I is the value of that register. And then we say if I plus 1 mod 8 0 do this probably at the end. Let's just see what that gives us. Not quite what I want. Oh, it's because the registers are not. So we want. Yeah, we'll do it like this. This is kind of cheesy, but at least that will line up then. Wait, why isn't that working? Shouldn't that zero pad? I thought it would. It doesn't seem to be. Well, it's fine. It is pretty annoying though. Oh, you have to specify how much to pad it, right? There we go. Okay, so what happens is we had 0 here, and then we did our execute, which caused us to load this address. Okay, that looks good. That looks good. So we'll print out PC here. Let's do, it's fine. What do I do? Too many arguments, right? And then we want a new line. Okay. Yeah, so that looks good. So basically what's happened here is we can see our PC after the instruction executes moves on, which is, yeah, just what we want. So now if we did another step, it should blow up because it doesn't know how to do this instruction. here. So yeah, let's do that one. So yeah, I think this will be kind of a good way to do it, because we can at least sort of, yeah, just like with the other stuff, we only implement the stuff that we can actually see that it's working properly. So this particular instruction is 6F06. It should be movel ARMP, I think it's this one. Yeah, 6F06, right. So it's movel ARMP-RN. And so what that's supposed to do is read from memory and write into this register, and then also increment. So this one actually, we're going to want to tell the pipeline that there is no memory access. Yeah. You might want to have a better way to do this, but for now this is fine. So then, this case, we're basically going to read the M memory register, oops, which we get from, yeah, these names are getting way long. Oops. Yeah. So this is M, and this is N. So we're basically going to read from M. Oh, so this is actually one where there's a write back, because it's going to write back into N. So we actually need to, yeah, so basically when we do an execute, we're actually going to tell it whether there's a write back or not here. So in this case, there's a memory access and a write back, like that, I think. So we can't actually do any work yet. We basically just have to tell it, we have to tell the pipeline that it needs to do a memory access. So let's see what that looks like again. Yeah, we have to basically tell it the type of access and the address, and potentially a value. For now, there is no value, so we won't do it. So we'll tell the type. The type should be basically whether it's a read or a write, and then the size. So I think this will be memory access write. Well, in this case, it'll be a read U32. Yeah. And let's see. In this case, it's a address. We know that the address is what is in RM. So that's going to be that. And then I think we actually increment RM now, like this. Is it 2? Let's just take a quick look at that. Move A. Oh, it's not move A. I'm looking at move L, but that's going to be up here. So that's it's this one. Yeah, so it adds 4. Oh, it's basically the size of the memory read. So let's get rid of that. So like that. So it increments our register, says that the pipeline, those next states are active, and then that's it, I think. So now we need to set up our memory access types. So this is our memory access read. And so if this is active, then we basically just take a look at what it's telling us to do. I have a feeling this might end up being like super slow because it's like separating everything out, but yeah, I don't know. Like I said before, I think before I worry about that, I'm just going to try and do it like the way where you just look at the doc and do what it says, and that should make it much easier to make sure that we didn't break anything. So memory access read U32. So at this point, we're going to do a read U32. Get our data. Let's call this X, and we're going to read the address from our pipeline. And we need to pass in the emulator, I think. Oops. Yeah. So that's the data. And then we write to the write back pipeline. So we write, oh, so this actually should have already written our register. So all we have to do is write the value. So write back. Where's our WB? Value. Yeah. So we'll just set the value to X. So we can actually just simplify that to this. Yeah. Okay. And so then that means that we also we set our register to N. Yeah. Okay. And then finally, if our write back is active, then I think all we do is we write to the register. So we do reg, and then we get the register from the write back pipeline, and we set the value based on pipeline, the value. And we'll put it after that. So I think that should be right. Yeah. All right, let's take a look at that. Of course. Let's see. Oh, this is a struct. This should be an enum. This is write back. What? Subscripted value is neither array nor pointer nor vector. Oh, it's reg R. There we go. Okay. So now we've executed. Yeah, this is a bit confusing because it's like you have to sort of know we're executing this instruction here. But in any case, what we should see now is that our M register, which was 0, gets incremented. So that's right. We incremented by 4. And then our R15 register should get written. That did not happen. Oh, no, it doesn't happen because it doesn't happen until the write back. So we kind of don't know what's going on with our stages. We definitely are going to want more information about like what's actually happening with our stages. So what I think I actually want to do is only print registers during execute, because that's the one where it's actually going to modify. Well, we kind of want to print it. We want to print like basically information about the stage that actually just executed. So what we should do is print our PC here, basically the where we fetched from, and this is our adder. So yeah, we'll just go back to basically pulling these values out, just because it'll make everything a bit clearer. So we'll say we fetched from adder, and we got it's a value. So this will be PC adder. And then stage decode, we kind of want to do is print out the operation that we decoded. So we'll basically say we got, no, this isn't adder, this is code. It's funny the types of bugs that you make when you are streaming your code. It's really funny. Maybe it's because I feel like I'm trying to go fast or something. I don't know. So what I want to do here is probably, what I want to do is disassemble the instruction, I guess. Yeah. And yeah, that should work fine. So we'll do stage decode, and we'll then do print inster e, and then like the other one we'll do it like that. And then for execute, this is one where, yeah, it's going to be useful to just print the registers. Let's see what that looks like. So we do a fetch, and that's giving us this value. Then we do a decode. Then we do an execute, and then print the registers, and I think that'll put. So it's a little bit weird because it's like we want to sort of space this data out a little bit better, but it's kind of readable. And actually, it might be more readable if I use a little bit of color. So what colors do we have? Let's use cyan. Oops. And then we'll go back to white. Do I want that after the new line? I think I might. I don't actually know how this works. And then this one, same sort of thing. Probably can just turn this into a cute little function, but just hacking for now. Just hacking. Yeah, so that's a little bit easier to read. Might be nice to put in a little of this. Yeah, that's better. I don't like this print registers now. It's funny how tweaky I can get about this stuff, but I mean, you have to read it, so it's better to make it. Wait, do I want that? No, I want it to be like this. Oh, you know, I see why I did it that way. Yeah. 1, 2, 3. 1, 2, 3. Why doesn't that print out? Oh, I want this to be like that, maybe? All right, well, that's good enough for now. Okay, so what we're seeing, and yeah, now I want the decode to be on the other line. Yeah. Let's just do it. Let's just do it, because that's going to be on one line. Yeah, so now you can see the decode there. That's kind of cool. Yeah. Okay, this is a little bit easier to read. So now what's happening is we do our fetch, then we do our decode. And we kind of want that to write what we decoded. So I'll have that be like this. And this will be code. And we'll pull that out here. Oh, but you know what's funny? This is wrong now. Because this is the PC. This is the current PC, but it really should be the PC where we read it. We read that instruction. So what I'm going to do is actually go back to the IF stage, sorry, the ID stage, and store off the proper PC there. Like that. Do we need to do that? We might not. It might be because I think, yeah, you don't actually need to store it. I think we can just basically subtract 2. And that's always going to be correct because we'll never be in a situation where we did a fetch and then we're doing a decode of something that didn't come right before, right? Because if the PC did move, then we wouldn't be doing a decode. We'd basically skip the decode. So I think that's right. We'll take a look. Okay. I kind of want this on the next line too. So I'm going to do like that. Yeah. Yeah, that's a little bit nicer. And honestly, now we don't really need to do that disassemble at the top. Which of course means that now we don't have to do all this bumping. Yeah, this is fine though. So we do a fetch, we get our value, then we do a decode, and then we do a fetch of the next one. Then we do an execute. What we kind of want is a separation between stages though. So we'll do like step. Like that. Yeah, that's nice. I like this. Okay, so we do our step. We probably want color for this too. We do our step, we do our execute, and then it shows the new registers. We kind of want to print that instruction again. Like that. Where do we do our print instruction? In this case, we don't actually care what the code was because that's not really the important part. Yeah, so let's just pull out the instruction here. And I think that's right. Yeah, okay. So now we have our execute. On a new one here. so we're executing this mov. Here's our new registers, which shows that we updated, yeah, we basically loaded this into R0, which is there. Then we do a decode of this guy and we do a fetch of this guy. Then we do an execute here of this instruction, which moves R0 forward. Where's our R15 now? Oh, that's the write back. Yeah, right. So if we stepped again, we would see the memory access. So let's print out something nice for that. In this case, I think we actually do want it to be based on the type of memory access. So we'll do we'll basically say what we read from and so this will be, and then what we actually read, which would be value. In this case, we're basically saying we read from here and we got this value. We don't have that step here, so we'll add a step. Okay, so it's going to blow up because we don't know how to do the next execute. Wait, why is it saying right back here? Oh, did I get an order of operations wrong here? Oh, yeah. It can't actually set... It can't actually set the write back to active because that would be the write back. Yeah, so it has to set... This is a little bit weird. We can't actually modify 2 stages ahead, I think. Yeah, so we basically have to sort of like funnel it through the memory access, which is a little bit weird, but again, we'll just do it. So this is going to set that, and so then now we have our memory access stage needs to also have the write back register that it funnels through. It's a bit strange, but I don't know. And actually, like I said, I think this is going to need to be an enum or something. I don't know. So right, rather than writing it there, we'll write it here. And then it's the job of the memory access pipeline to basically funnel that through. So it'll basically say this reg is equal to the memory access's write back register. But it doesn't do the write yet because it's not allowed to. Yeah, I think that's right. Okay, so now we're not doing the write back, which is good. We do our memory access, which basically reads from here and does that. And then if we did one more, we would do the write back, but we can't because we don't know how to execute a branch instruction, which is this guy here. So actually what I want to do is instead of blowing up here, I kind of want to print out afterwards, which means how do we do that? Yeah, we'll just do something sort of cheesy like result equals okay, and then this will be result equals error. Someone's making something good. It smells good in here. And then if result equals error, then we say, do we have an unreachable? Yeah. Yeah. Okay, so yeah, so it's basically saying, okay, I don't know how to do the branch instruction, but it looks like everything else is looking pretty good so far. So now, if we just say that the branch instruction does nothing, which is wrong, but it will allow us to sort of see, whoa, 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 stop, stop. Now we can basically just say, okay, yeah, we did it, but we didn't. We should see the write back now. Oh, we didn't step enough. Yeah, there's the write back, and it's not actually writing anything yet. So let's do that. Basically, we know this is our register, and this is our value. So we have our register equals value, and then this is our write back. So we'll just say r d equals. Should make a macro for this maybe. Reg equals val. Oops. And let's print the registers there too. I think print registers adds a new line at the end. This is kind of silly. Okay. So now we do our write back, which sets that, and there we go. Cool. So now we actually want to actually implement the branch. So let's see, how long have I been doing this? Let's see. About an hour and a half. Okay, I'll go for a little more. So let's take a look at BRA. So going back to our doc, BRA instruction. Is that it? No. BRA instruction. Okay, here we go. Oh yeah, so this is going to have our delay slot stuff, which is a little bit weird too. So, yeah. So basically the way the delay slot works is that we have our pipeline, right? We have an instruction that's ready to go. In this case, it's going to be the this LDCL, right? That's the next instruction that would execute. And rather than throwing it away, like what would have happened because of our pipeline. We're basically saying do the branch and also do that next instruction, because otherwise you're going to have to throw it away. Because it actually will create a bubble, I believe. Actually, they're expressing it via this delay slot, but my guess is that actually it just does it, right? Like it's just using the normal pipeline to do this. So that's BF, yeah, unconditional branches. Yeah, so there's the delay slot. What? The branch destination address is calculated in an EX stage. Well, it doesn't really matter where you calculate it, right? Instruction following the unconditional branch, that is, the display is fetched and not discarded as the conditional branch instructions are, but is then executed. What's weird is that it executes the branch. This is the delay slot. Yeah, so it can't do the execute here. But interestingly, it also doesn't do the decode here. I wonder if that really matters. Well, I mean, it does, because we actually yeah, that's weird. Note that the ID slot of the delay slot instruction is stalled for 1 cycle. The branch destination instruction starts its fetch from the slot after the slot has the EX stage of instruction A. Yeah, so it basically does the fetch from, this should be the new location. So, So the proper way to do this then is to update the PC here. And this would be updated to the pipeline D, because that's the actual destination address. And then we actually have to we basically have to say don't do anything else. Don't do the decode and the fetch. But then we have to but we wanted to so we basically want to disable the pipelines. We want to disable the execute pipeline here so that we don't basically re-execute this. And then when the decode comes around next time, it'll re-enable it. Like here. So this is going to do the proper branch. And then the decode actually has the delay slot in it already. It has the correct PC and it has the correct code. So it could just execute next time, but it shouldn't execute this time. So we need to have a way to say it's active but delay everything. So this basically just needs to return like a stall. So we'll call this like a stage result, and this will be stage result. Stage result. Okay, we'll just call it for these instructions, yeah, so what we should do is do stage result, result equals stage result OK, and this will just return result, and then this result we can get rid of, because now what we'll do is we'll say this will be, we'll just call this unimplemented. I mean, it's a little bit weird, but like this will go away eventually. Unimplemented. And then we can return result. And so then this will actually be result equals stage result stall. Yeah. So let's add those stages. Stage result. Okay. This is implemented. This is stall. So then we basically say if it's not stage result stall, then we do those two. Sorry, if it's not equal to that. So basically what we're saying is if the first time we come through, well, let's just take a look and see what it does. Yeah, it's not regs, it's reg. Okay, so what happened here was what? Oh, we didn't. Why didn't we print our execute? Okay, so we do our stage execute here. Yeah, okay, cool. So this basically says update the PC, which it did. It does the write back, because that's still valid. It does the memory access for, wait. It does the memory access again, that's wrong. This should actually set the, this should set the write back to inactive. So in general, yeah, that shouldn't touch that. In general, we'll want to set the next stage to inactive, I think, because a lot of these won't do write backs, or sorry, won't do a memory access. So in this case, we'll say don't do it, but if we do have a memory access, then we'll say, okay, set it to do and load up the value. And that will prevent us from doing an additional memory access here. So we did our memory access, we did our execute, we do our write back, then we do our branch execute. No, we already did our branch execute. Why is this doing it again? Right, so basically we need this to disable. I think I probably mistyped that before. Yeah, okay, here we go. So we do our branch, we do our write back, then we decode the next one and fetch the next instruction, which is at the new location, or branch location. Yeah, that looks right. That looks right. Okay. Then if we do one more step, now it's going to blow up on our LDCL, which is our delay slot instruction, and we still have this write back, so we need to disable that too. I think in general, yeah, we want to. we want to disable our own pipeline. We might want to, yeah. It's weird because it's like you have to sort of think backwards. So do you always want to basically disable yourself and the next one unless it's... I mean, in this case, we always want it to be true, so that's fine. But I think in general, we want to actually... No, I don't think we need... Well, I don't know. I'm not sure about that one. This one we definitely want to disable because it doesn't happen most of the time. I think the thing is that most instructions go through those three stages. It's just that memory access and write back don't always happen. So we'll disable write back here as well. So yeah, so now we just get this execute here, which fails. So this is our write back. That stores our variable. Then we do our execute here, which would be our next step. So yeah, we'll do LDCL. Oh yeah, and so this is already showing me that we need our write back to be able to write into a different register. Yeah, since all our registers are 32 bits, I'm starting to think that rather than having these separated out, it actually might be easier to just have a big pile of registers, and then we know if we have a specific register, we give them an enum. So what I'm thinking is something like we have, where do we put this? Here's one. Register. So we'll basically have GBR equals 16, and then everything else goes from there. So register mockle, oops, what am I doing? Mockle PR. PC is special, so I'm not gonna do it that way. And then SR. Yeah. So then so we'll do num registers. Like that. But now this is making me think that rather than having a structure for this, we just do like this. And rather than giving these, well, I'll do it like this for now. Okay, let's see what breaks. So now instead of doing it like, oh yeah, reg I. Well, okay, so this just means this is basically the structure of SR. So I have to see what SR has in it. This way up here. Yeah, so the default SR, it's 4 through 7, so that would be register SR equals else is broken. It doesn't like PC. Oh, wait a second. Ah, yeah. Okay, so we'll just do it like this. PC is really important, so it's fine to not have it on that. So this is going to print all of our registers now. But we kind of want it to... Yeah, I don't know. We're going to want better names here, but we'll do that in a sec. So that's reg 0. That's reg m. That's reg m. That's PC. That's reg. Okay. Now. Okay, so everything seems to be okay. There's our fetch. But now we should be able to do a write back into VBR properly. So what that means is that we can go and add our next instruction. And just because I like to be anal about these things, let's put these in the right order. So ARP is above move A, which is kind of weird, but whatever. For BRA here. I find that just having like this order makes me like be able to think about the code and not, I don't know, reduces my code stress, we shall say. So the next one we want to do is LDCL VBR. So it's this one here. And so that's L, so it should go here. So that's the instruction we want to have execute. For now, we'll have it do nothing and see what it does. So yeah, there's our execute. It would have written to VBR. Actually, it won't. It won't do it until the write back. But you can see now there's our decode of the next instruction, which is one we haven't implemented yet. This is other move L. That's fine. So now we have our ARM PVBR, which is actually very similar to this one. So what we'll do is we'll pull out our M register, because that's all we get for this one. And it's a read, just like the other one. In fact, I think a lot of this stuff is the same. The only difference is that our write back reg is now register VBR. Like that. And yeah, there's like a lot of duplicated code here, so we're probably going to want to clean that up. But for now, that's actually pretty cool. So what should happen is when we execute LDC LVBR, we should load, yeah, see, and so this is already confusing because it's like these are actually not numbered registers, these are named registers. So what I'm going to do is add a little structure for registers, just names for them. Registers equals register, R0. So there's we want to do IPA. Like that. And then the last ones are VBR, VBR, mock, mockle, PR, SR. Like that. Okay, and so now we can use those names here we just do reg names like that. What do I call it? Reg name. Yeah. And we can do the same thing in print registers. So rather than using the name here, we'll use reg name. Like that. Okay. So there's our names. And yeah, this is really annoying because it's like it's not formatted nice anymore, but that's fine for now. So yeah. So there's our VBR, and it looks like, yeah, it didn't have the write back yet. So if we do one more step, we should do the write back to VBR. What? There's our execute. Oh, there's our memory access, and then we have to do 2 more steps. So actually what I'm going to do here is, what do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Rather than have to do this, I'm just going to do so the trouble is that and this is going to be one of the issues that is going to happen for a while, is that like as we're executing instructions, we're not going to actually be able to see the full effect of the instruction until we sort of implement the next instruction and so on. So it's like the pipeline actually sort of gets in our way, but yeah, it's fine for now. So the instruction that it doesn't know how to execute is this one. And again, I'm just going to do the same thing that we did before, which is find that instruction and then just stub it out. So in this case, the instruction is movl a rm rn, I think. This one. And just to make sure, that's 6 with a 2. Is that right? Movl, where's our movl? No, that's D4. So that's probably the easier way to find it. Oh, it's this one. Okay. Okay, we'll add that one in. Move ADPC, move. Oops. Cool, there's our write back. And it updates VBR. Very nice. Yeah. We're definitely going to want to come up with a nicer way to do this, but for now this is actually pretty good. One thing that would be cool as well is being able to see like which register actually got updated, but I don't know, like all this kind of stuff is like, yeah, nice to have, I guess. Okay, so this instruction, I believe, does a read, and then it's just a straight up read. Yeah, I think it's just a pretty bog standard read. So it's going to look very much like these ones. In fact, I think it's identical to this, with the exception that it doesn't increment the register. So I'm going to do that, but yeah, I'm starting to see that like this can definitely be factored a little bit nicer. Oh, and this is actually, no, this one is actually a little different. I take it back because there's no M. It's actually reading from D. So this should actually be pulling the address from the pipeline x insert D, which is D here, this doesn't get incremented, so it actually is more like this. So that's the address to read from. That's the right register to write to. Yeah, I think that's right. And then the cool thing about the pipeline is that the rest of the pipeline just works. It should just do it. So we got to, that's our write back for VBR. We need to step another step. Yeah, and it's not going to step because now it wants to do this one. Yeah. All right. So that's a move immediate. And again, I'm just gonna stub it out for now. Okay. So there's our write back for this one. Is that right? Okay, so we did a memory access at 498, which was here. That's the value we read, and then we write back to R4. So yeah, this is the instruction, and then we finally finished it back here. That looks right to me. And then we have another branch. Yeah. Okay, this is looking pretty good. This is looking good. This is like a good structure, I think. And we're kind of about in 2 hours, so I think I might quit. Maybe one more instruction, because I feel like this one should be pretty simple. This one's cool because it's actually, because it's moving immediate, there's no memory access, there's no write back. So we just have our register here, so we can actually do, we get our value, and there's no read, there's no memory access or anything. The only thing we have to do is write that, I think. And because we set our memory access stage to be inactive by default, that's what this will do. So it actually might be nice to pull out some of this logic, but we'll see. So what do we got? There's our move 0, and it would have executed here. No, it should have executed here. Yeah, so it basically cleared it out. Yeah, there we go. So there's our write back, and there's our clear. I'm actually going to remove this one because our write back is actually pretty straightforward, and it's just cluttering up the output when I do a print reg. Yeah, that's nicer. And then we'll add a additional space here. Yes, look at that. Pretty. Okay. So now, there's our VBR write back. There's our memory access. There's our next stage execute. There's our decode. We execute the next branch. That basically causes a pipeline stall, which then, but we still decode the next instruction. And then we fetch the instruction from the new PC, which was the one we got from here. So if we do one more step, what we should see is the execution of that next instruction, which is unimplemented. This is actually going to be a write. Let's see. Yeah, we haven't done a write yet, so that's interesting. That one, that'll be a memory access without a write back, because it basically doesn't have to update any registers. So yeah, let's try that one out because I kind of want to see what that looks like. Basically at this point we have, Yeah, everything going through pretty well. So I'm going to see what this one is. This should be movel rmarn, I think. rmarn, that one. Just to make sure, that says that's a 2 something something 2, 2402. So that looks right. So yeah, I'm gonna sort these all later because I can totally not keep track of where everything goes. Move L rmarn. Okay, so in this case we still pull out our m and our n, and we have all this stuff. Our write back reg is n, same as before. We don't increment. Our address is no. Our ax. We have no write back. We just have to basically write our value. Oh, so this is a different type of memory access. So now we have basically write U32, and when we have a write, rather than having a write back register, we actually have a value that we want to write to memory. Oh, and that's what I had here. So we can actually do that, because we either have a write back register, which means we're doing a load, or we have a value we're going to write, which means we don't have a write back register, I think. That might not be true, but for now it is, so we'll do it that way. Yeah, so then we set the v32 value to the value we want to write, which is rm. And then on our memory access pipeline, we add a new case for write U32. And I don't actually have a function for this, so I'm just going to do it like that. But the important part is there's actually no write back, which means we actually want to disable that here probably. And again, I think the same as the other case, we want to actually set MA inactive as well. Oh, I see. This one's already kind of done it. But that's for the next instruction. That's for this instruction. Maybe it doesn't need to do it. I don't know. I have to think about how we want to handle the active flags. But in any case, this is the address. And then we get the value. So we're basically saying write this value to this address. And like I said, we don't have a function for that. Just yet, but we'll just stub it out. Why? Did I not have that assert before? I'm not sure. It's weird. Okay. So there's our write. And then we execute it. And what it should be executing is writing R0 to... Oh, we didn't actually do our memory access stage. So we just need to bump that one more. And there we go. No. What is this? That's garbage. Yeah, this should be write U32. Like that. So now we write 0 to this address. And then we start executing the next thing. Okay. I think this is actually on a pretty good path. So thanks for watching. Yeah, hopefully next time we'll have a bunch more instructions implemented. But yeah, I think this is basically the right structure. Looks like we can pretty much do what we need. I guess we'll see once we get into some more crazy instructions. But for now, this looks like basically what we want. So thanks for watching, and I'll catch you next time.